Hey, hello everyone. Welcome to the second week's practical session. We will today explore the basic building blocks of neural networks and use what we talked about in the lecture to create some fully connected neural networks in Keras in Python. We can start with the like more or less unofficial homework from the last class, which was to read the article about creative adversarial networks. So I wanted to ask about or talk about the Khan paper, which is here. Did you get to read it, or at least skim through the content, and sort of what do you think about it, actually?
Yeah,
Go ahead, Josh.
I read through most of it. I kind of skipped the technical section. I thought it was really cool, really interesting, and the results are really, really cool. I find it kind of hilarious with all of these papers when they insist on trying to analyze the artistry of these kind of systems. I don't think there's anything wrong with just making images and like exploring that the creativity in like making novel images or something that's feels new. And I like their kind of approach in exploring that is really interesting. But the kind of analysis of how artisty or arty it is, I find kind of painful and like overly scientific.
Yeah.
But yeah, in general, the whole system is really cool, and their approach to it I found interesting, and the results are really lovely. I think they're really nice images.
Yeah, and I think it's crazy because it's from 2016 or 17. Yeah, 17, middle of 17. So it's already old actually, but yeah, it looks pretty good. Okay.
Yeah, same as Josh. I thought it was quite funny how they sort of measured the artistry of art in terms of its popularity. So like, I don't even know if that's the correct way to analyze art per se. And also they said that that like art is not creative. This model that they built somehow maybe is. I don't really see how it's that much different from the original GANs.
Yeah,
it's just a tool in itself. Like,
yeah.
I thought it was conceptually pretty interesting how they used two kinds of discriminators that seem to be in direct opposition to each other. I couldn't really parse the math for that, but I like the concept.
Yeah. Yeah, the math there. I think, like, if you want some help with the math, I think sometimes even reading the previous papers will help, because that's the one which sort of standardized the math notation, and so the later ones will only like show the same, but then added their own losses in there or something, so their own functions, and so it is maybe quite hard to parse. But sometimes the first paper, well, even though it might be more mathematical, the notation there at least is explained. I completely agree with the with you guys, in the sense that it's funny to see that they sort of need to they feel the need to have to define something, and I think what they are doing is trying to kind of differentiate between their work and the work previous to that. So that is just I guess because they were afraid that someone would attack their work as hey, this is just a gun trained on this. Okay, it's an art data set because you sort of picked a wiki art wiki wiki arts as a data set, so it's sort of novel images, but then what is the new thing there? So I think in that cases there was a push from their side to like sort of try to define that boundary, but then still I agree that it's quite actually interesting what they did with the signals that the discriminator is giving the generator. And like, I appreciate that we didn't talk about this yet at all in the class, so we will touch upon that later actually. But it's still kind of like a nice addition to what existed before. Yeah. I also think that it's interesting that they chose like the task of they didn't stop at something easy and small. They just went for the ultimate goal almost, to have a machine which is an artist, sort of, right? Almost. It's the same as if as when you are talking to a AI scientist and they would start talking about creating actual general AI. So not something which is sort of like an algorithm which can optimize some problem. That's what we call AI now, but it's sort of like it's limited intelligence. It's just using some smart algorithms there. Whereas to have the sci-fi idea of having like a companion that you can sort of talk with and then just give them any sort of questions, and they are even smarter than humans usually or something. That is the goal of general AI. And there is a huge distance between these two. And so also between when looking at just guns and having them generate novel images, that would be the sort of first category, and them trying to have a gun which is actually creative. And I think creativity sometimes as well is actually described as like one of the necessary things that the general AI would have to have. So it's an interesting task that they want to go there. I don't think that they went that they actually got there. I think it's a nice approach, but even with all the tricks that they did, they proved to that they created a very. So I think what they did is very creative act, because the whole programming of that system is really novel and really creative in programming it. But I don't think that like they created a that the thing that they created themselves could replace humans in generation of something, right? And so I think this is a this was 2017, right? Yeah. I think maybe sometimes in like newspapers you would read about this approach more, but what we will maybe focus more in this class will be not on really the philosophical question if we can create something which is creative, but actually in maybe and which is creative on its own. But we will more focus on the aspect of maybe having some tools or something which will help us being creative with that. So I guess you change the question of is this a fully, are we creating consciousness into yeah, this is a cool tool and it's something that we can use to be creative with. And so you're sort of abstracting the need to do artistic stuff with that, because you say that, oh yeah, I'm the one doing the art with it. And I think this is enough, sort of, so we don't have to strive for the ultimate goal of creating a system which would be on its own creative. Let's move forward, and let's now look into today's practical section, so the programming part of the class. And in order to do that, we should follow from the code I have on the website. So if all of you could just go into our Git repo and then open the task or like the starter code, which is in the second week's folder as a IPython notebook. So if you remember, in the class we went through the fully connected neural network as a model, and so this slide actually is something that we ended up with. So yeah, I think if you remember, we were sort of using showing a online interactive visualization of the networks. And so I was showing this in the lecture slides, so I will not explain it too much here. But let's just say that there is a neural network running here that has been trained to recognize numbers. And so if I draw it something, it will correctly classify them. And so all of these lines and all of these points mean something, and what they mean, and so how they are created, we will sort of explain today in the practical section. Last thing to note is that the model here is created by having neuron 1 to neuron 300 in the first layer, and then neuron 1 to neuron 100 in the second layer, and then in the last layer this has to be the same as the amount of classes. So the model is made of 2 layers, or maybe 3 actually. This can be considered output, or it can also be considered a layer inside it. So let's say these are 3 layers. The first one has 300 neurons, the second one has 100 neurons, and the third one has 10 neurons. Yeah, let's make this happen. Let's create it in the code. Okay. So in order to do all of this, we will have to import some libraries, and I just imported everything here at the start. The most important library is called Keras, which is a machine learning library, which is quite user-friendly. I was starting on it, and I think everything I was doing up until now was more or less possible in Keras. There are some things that, like when you want to hack the model somehow, you sometimes need to maybe use a different language, or maybe especially when you are using some other people's codes, you have to use other libraries as well. But if you are creating your own one, Keras is pretty powerful and also much more user-friendly than TensorFlow, as I found. So I think it's a good one to start. Okay. And also there is a lot of like examples and everything on this site on the Keras website. So yeah, let's start with Keras. From there we will be using its so yeah, there's some just to help people. They have a handler to download the MNIST dataset, and then there are some functional things here which we will describe later. So these will be created, used to create the models and the layers. Okay. Then we will be using the matplotlib the same way as last time. It's just a plotting library, and NumPy, which is a sort of linear algebra handler to make some computations easy, because they have a lot of these formulas in there already. Okay. So after the lesson, I think some of you might be slightly. It was a lot of things, but at the same time, we are still sort of in the start of the whole machine learning course. So even the models we are describing are relatively simple. But there are a lot of concepts that I have to explain, so it took a long time, I guess, and the first lecture was pretty long. But the lucky part for all of us is that when you are actually converting all of that, what we were teaching about in the lecture, into code, it's surprisingly easy, and we don't have to really re-implement a lot of it. Yeah, exactly because the libraries like Keras exist, because they sort of implemented all of that before. Okay, so let's start with the code. Let's start with loading the dataset. Okay, what happens here, and I will just comment everything that I don't want to use right now, is that we download the MNIST dataset and just load it into these 4 variables. Yeah, it will take some time to connect, and then it will be downloading the dataset, but yeah. What you might remember from the class is that we have some. Oh yeah, I didn't import, right? Cool. What you might remember from the class is that we have been using the terminology sort of to call some things X and something Y, and in this case, all of X are the inputs, so that would be the images, and the labels are usually referred to as epsilon Y. So when you directly just download it, oh yeah, not to have this. What happens here is that we just load these into these actually 4 variables. We are splitting the data into training set and a testing set, And this is something we have not yet touched upon in the class, but I will briefly explain it here. We talked a little bit about the the capability of a model to generalize. So being able to work with data that it didn't see before, and that's a big thing because sort of like you're training the model on some data that you collected, and then eventually you want to send it out into the wild. So create an application on a phone or something, and then expect that people will be taking all sorts of pictures of that and using that model. Well, it's hard to predict what can happen when people try to feed it some new data that it didn't see before. And so the way how scientists approach it is basically if you have some data set originally, so the MNIST data set, they just split it into just 2 bits, and one will be the one that the model is training on, and the second one will be a one that will be used to evaluate it. So these images in the test set is something that the model will never see when training. So that's the only way how to kind of say that that we are testing it fairly, because we are testing it on something that it didn't see before. And yeah, this is actually really helpful because it's already telling me the shapes, and so you can see that we loaded a 60,000 images of 28 by 28 pixels, then 60,000 labels with just one number for each. And the same with the test set, but only that there is 10,000 of samples in there instead. So we also mark that we have 10 classes, which means that we have numbers from 0 to 9. And we have to do something with the data, because right now in this shape, it's hard to work with for a couple of reasons. So if you remember in these slides, we were talking about flattening the data, and then also in converting the label, which was just saying 3, into some vector representation. And that was the one-hot encoding or one-hot vector representation. And so, yeah, hopefully this is simple to understand. So if you have a some amount of classes in your dataset, you change the label of that class so that every one of these numbers corresponds to one individual class. And so if we had 10 classes which corresponded to the numbers of the handwritten digits, then each of these will sort of correspond to one of them. And actually, like, best is to just look at this visualization. This is the one-hot vector, sort of. So 1 is the number that we want for the prediction to be at the output that is the most is deemed as that's the one that the image is classified as. Okay. So, well, just to bring it short, what this means is that we have to somehow convert this data into the flattened vector, and also we have to somehow convert this label of 3 into these vectors of one-hot encoding. So if we were to very randomly just print some samples, so let's print the first image in the training set and then the first label in the image set or in the MNIST set, then we will have bunch of numbers. This represents a number. This represents, actually you can almost see it here, right? Because these are the pixels, so the pixel values. So this is the image, and then the label was 5. Yeah, so apparently there is a 5 here. So this is not the best way how to show it. There will be some visualization later as well, but this is just to show the raw data. Okay, and so what we need to do is to do 2 operations on it. One would be to flatten the data, so convert it into a vector. So each one of the 28 by 28 images will be flattened into a 784 vectors, and that's basically 28 by 28 evaluates into this. So that's why it happens. So the way how you do this in code is that you will use reshape, which is something from NumPy, which it figures it on its own what you want. So if you are working with 60,000 28 and you tell it, hey, reshape it into 60,000, and then here this number, it will figure out that you actually want to flatten these 2. last coordinates. So that's the trick which will flatten it. We want to work with it as floats. I think in here we were loading it as integers. And then what happens also is that we divide it by 255. Basically, we convert the numbers that we can get from 0 to 256 or 255 into the region of like in between 0 and 1. So we don't want to look at the images as integers actually, which would have RGB, or in this case, I guess just a gray value between 0 and 255. We want it to be in some float number between 0 and 1. Why we do that is because when weighing all of those numbers, it's much easier to work with numbers which are somewhere around like going from 0 to 1. Yeah, this is like a small detail, but actually, if you didn't do it, it would usually mess up the training quite a lot, because for the network to understand numbers which are really far away from each other and really large in the size, you sort of need to do some sort of normalization. Okay, and this is a simple one actually. So we pre-processed the input data here, and then we will also encode these numbers. So we had 5, and that 5 would actually turn it into 0, 1, 2, 3, 5. So the first label should be turned into having a 1 here then. And so thankfully for this, we don't have to write it on our own. There is a keras.utils.to categorical, and it will convert it from basically from a number. So from I'm like, this looks like it's a string. It's actually an integer number, and it will convert it into a vector. So something like this. Okay, and so yeah, this happens. We can let it run. We can even override the original variables, because we will never be working with this raw form of the data. And so let's look at the data. So this is just showing the shapes. Well, these will be the same as what we saw before, except that this is flattened. So is this something that we expect? Well, I guess, is this something that surprises you? Would be the question. Hopefully not. So this is something that should correspond to this image, right? So from 1 to 784, and then from actually from 0 to 784, and then from 0 to 10. Okay, so this should be correct. This number is the amount of samples we have in each of these, so the amount of images, basically. And let's have a helper function which will show us or plot us the image as an actual image, actually. So it will reproject the vector back into something that we can see. And then let's show any one of those numbers. So this was the first one that we were printing before, and this is how the data in MNIST looks. So if we say, okay, let's see some other one, there is some 9, let's see some other one, there is some 6, let's see some, we can basically inspect all the numbers in the dataset. So this is actually 1 as well, right? This is a messy one because some people write it with 1, some people write it just like this. Okay. So this is all the data that we have right now. Okay. And this is not exciting at all so far. We still need to create everything, but this is important bit because we have to have some data to work with. Okay. So how to actually create a model? Well, so here will be some code that we are sort of copy pasting from some example, or we can just copy paste it from documentation, and we can just reuse it. So we are importing the dense as a layer. Dense means the fully connected layer. Actually, they call it densely connected layer, or fully connected layer, or just dense, sometimes dense layer. And so this will be the layer inside the model. And to just start it, this is a object which holds nothing so far. So we just created an empty sort of model. And if I just print it, it will just tell me, hey, it's an object. But Keras has a sort of nice way to visualize the model that you are working with, and that is the command of model.summary. It even pops here. And so if we do that, it will print it out as a sort of, it will sort of visualize whatever is in that model. And if we try it here, it will shout at me because there is nothing in there yet. It's actually empty. So yeah, that's why it didn't work. So we need to add something to the model. So this is a sort of empty handler which has nothing in there yet, and we need to add layer by layer what we want to sort of, how we want to build the architecture of the neural network. And so if we refer back to this, we sort of need to add a layer, add the first layer, and then add the second layer, and then add the last layer. And so all of these are the dense layers. As we were looking here, this one has 300 neurons, this one would have 100 neurons, and this one would have 10 neurons. So we sort of will copy that as well. We will sort of do it here. So the way how you add a layer in it into the model is just saying model.add. It will figure out where the model is at kind of currently, and sort of just add at the end of the current model will just start attaching whatever you give it. And there has to be something here, right? We have to actually a layer. There has to be some layer there. And so we will work with the dense layers. And so we imported dense here. And so we can just create a new instance of the object called dense. I mean, we can call it also just like first layer to be programmatically more clean, but no one does this. You can do something like this, and then start creating the layer here, but then it just creates more lines. And so in here you can see all sorts of things that you can set up for the individual layers. The most important bit that we care about is the units. The first one, which corresponds to how many neurons we actually have in that one layer. Everything else is sort of not super important for us. The only one we will also try to change is the activation, because in here we can change the function that will be used in the activation in the neuron. So if you remember, somewhere far away here, we talked about. Oh, I guess it was somewhere in the homework, maybe. Nah. Oh yeah, somewhere here. We talked about this being a function that we called an activation function, which is something that sort of somehow weighs the inputs. So it weighs it in this way, sort of like whatever comes in here, we then use the function to process it and to send something out. And we also talked about the fact that this one, the min x0, is called ReLU, rectified linear unit. So there are a lot of types of activation functions that we can use. I think even Keras, probably in the documentation you will have a lot of them. So if I search for Keras activation functions, it will probably come up with just a page full of activations. And so you can have some ELU, you can have softmax, you can have CELU, you can have soft plus, soft sign, ReLU. This is the one that we will care about. TANH, sigmoid, this is the sort of original one, but maybe not the one which works the best, etc., etc. Right? There are a lot of them, and just to add to this, you can sort of create your own function that will then be the activation function. Well, so that's the thing that we will be putting here into the activation. Okay, so I would just add 300 and then have to write something for the activation. I will use the code that I prepared here because it's more clean. And so do just the thing that I was explaining. So model.add a dense layer, meaning fully connected layer, with 300 neurons. And each of these neurons will have a ReLU as an activation function. So that will be the one which is maximum from 0 or x. And in the first kind of the first layer that I'm adding to the model, it has to be a one which has a parameter called input shape, where I need to give it the size of the input. Well, that's because when I'm creating the model, it doesn't know what it should have as an input. And sort of in this step, I'm adding the whole layer of 300 neurons. And it sort of needs to know how many weights each of one of those neurons will have. So yeah, let's do this. And I think now we already created the model which has something in it. So we can now even try to start this function, model.summary, which I will put here. Yeah, okay. Okay, great, it stopped shouting at me. So we created our first model, which is here, and we added one layer into it, which is this one. And sort of this visualization tells us this is what happened. Hey, you have a model called, it's some automatic name, and these are all the layers that are there. And we just added one, so there is dense one. The type is dense, which is a fully connected layer. Its output shape is none. This means it doesn't know how many samples are we feeding it with, and the output would be 300. Well, I think this doesn't know how many images are we feeding it in total, so the 60,000. So this would be some, like, it would be depending on. Wait, is that true? Yes, yeah, actually, because like if we feed it, yeah, because how for one image that we propagate through, this will be one, and then I will have 300 outputs of this network, and this is some calculation that is a strange number that I will explain in a bit. So let's see into the visualization. These 300, right? So the neuron network that we created just right now has just this first layer. So it has 1 all the way to 300 neuron. And so the output at that moment, sort of from this second or from this first layer, is no longer this flattened image, but it is these neurons, and each of them has their own I1 all the way to Y300. So that's why we have the output shape of 300 here. So you might be confused about this strange number of parameter. So let's copy it. So this refers to how many parameters we have in this just this first layer. How many weights sort of we have in this first layer. And if you inspect every one of them, you can see that every neuron has always that many weights or that many parameters, how many connections it can even have with the previous layer. And so the previous layer in this case is all the pixels, so 784. Sorry, it was written here, 784. And so each neuron will have 784 connections. Plus one, but that's sort of like the one that I just briefly mentioned, and that one is not that important. So let's calculate this number. If you look at this divided by 300, so just to inspect how many, because we have 300 neurons, so inspect how many parameters does this evaluate into for one neuron. Okay, this is 784 plus 1. So this number is something that we got by multiplying this number with how many neurons we want with this number of how many inputs each one of those neurons will have. Right. Okay, so this is a completely boring model because it has nothing in it yet. So I will erase this and I will start adding further layers. So I can do this like this, do it like this. Model.add dense 100. This is a second layer, so it no longer needs to know the input shape. It will calculate the input shape from the previous one. It will know that the output shape of this layer will be 300. So it will sort of consider, okay, I have to connect 300 neurons with 100 neurons from the next layer. So let's do it. Okay. Again, let's print it out. And this is the same as we saw before. Basically, we just added another dense layer. This number should be 300 by 101 because we have 300 connections from before, plus 1 actually because we add the 1 which is always fixed times 100 because we have 100 neurons in the next in this second layer. So this should evaluate into this. Awesome. I mean, no one actually cares about the number of parameters. I'm just sort of like trying to decode everything that's on this slide. Okay, so let's continue. And then finally, we will be adding the last layer, which will have just the 10 neurons. Yeah, this is a number with 10. So in this case, I'm also changing the activation function. It's no longer a ReLU, but it's a softmax. And this means that basically this is done with the outputting layers. And I am telling the model that at that moment I wanted to sort of normalize all the outputs that it has, and then divide the numbers so that they sum into 1 in total. So all of those, every image will sort of produce a vector of 10, and softmax means that it will either scale it up or scale it down in a way that some of those vectors will evaluate into 1. And so the reason why I want to do this is that if I am feeding this model that we are creating here actually now, if I'm feeding this with 0 or 1 filled vectors, 1 hot encoded vectors, this output, the one after softmax, will be matched with this vector that I'm feeding it with. So I am sort of forcing it not to, I'm converting it into the same region. So then the error function that I'm calculating here makes sense. If I didn't do it, it would not make sense much. It would not make much sense. Right. Okay, so let's do this. And then let's finally print out the last one. And that's what we have actually. So we added 3 fully connected layers. That's 1, that's 2, that's 3. By the way, you can rename them in here and everything, so then your models become more parsable. But anyway, this one has 300 neurons in it, and so it outputs 300 numbers. This one has 100 neurons, and so it outputs 100 numbers. And the last one is just 10 neurons, which output 10 numbers. Okay. Another way how to show this is to show it slightly more visually. This is a nice debug output, but this is a plot which will show it as an image. I mean, it says more or less the same thing minus the parameters, which you could, I think you can still like change something here and it will still show the parameters numbers. But this one also includes the dense 1 input layer, and so this one is maybe showing slightly more than this one because it's showing that it expects it to have inputs of this vector and then connects the same way. All right, actually it shows even like more shapes here. So this one expects inputs of 784 and then outputs of 300, which is sometimes handy to actually see. Yeah, when we are calculating the parameters or something. Okay, so this is almost it in terms of creating the model, and we have not trained it yet. Is everyone still okay with this, or sort of is everyone following up on this?
I have a quick question. When I type in model.summary, like after adding the third layer, I get dense 1 to dense 8 instead of dense 1 to dense 3, which I saw on your screen.
So,
and I wasn't sure why this was happening.
Yeah. So the fact is that the model always kind of keeps everything that you add into it, and so it keeps it in mind. And so if I were to then rerun this one line several times, each one of them is then taking whatever the end of the model was and then adding a new layer there. So even though I'm sort of writing it 1 here, second here, second here, second here, if I run some of them multiple times, it will actually create a model which has many kind of rubbish layers there, right? And so how to fix it actually is easy. You just have to erase the model and create a new one basically. So rerun this first field, then the model is empty, and then only add the first one once, add the second once, once, and the third one once, and
Okay.
then you would have it here. I think this is some like this is the plague of using IPython notebook, because then it separates the execution of the code with like with what's actually happening. So how to fix it? You could also have all of these in just one of these fields, and then you couldn't really rerun some of the fields multiple times. But,
okay, thank you so much.
Okay, cool. It's actually quite smart, because at every moment it figures out where to connect the last layer that you ask it to sort of append to the model. So it's nice. It's not super complicated. Okay, cool. Any other questions? Okay.
The number of neurons in each layer, is that kind of just an arbitrary selection? Is that just kind of just based on intuition a little bit?
Yeah, so basically no one knows upfront what the model will like what is the best number for the model to work with. There is some sort of intuition behind there, and that hides in the amount of parameters. And the almost unsaid rule is that the more complicated data set you have, the more parameters you need in the model to learn that. So if you imagine if you had like a neural network which had just 10 neurons, then I can create it even actually. So let's say, yeah, we will hack in some slides here. So if I create one which has just one neuron, let's say, and then just print it. Oops, let's say two maybe, just two, and then print it out. Then we know that there are two neurons, and even then they have quite a lot of parameters. But these two neurons need to learn this sort of really complicated differentiation between numbers from 1 to 9, and so the number of parameters, sort of the parameter is the I guess you could relate it to a brain capacity of the model. So the larger it is, the more it can memorize on its own, and the smaller it is, the less it can memorize. What becomes a problem then, if you choose too large model which has too many parameters, it believe it or not, it can sort of remember all the samples from the training set that you showed it. So it can remember, if you mess it up, sort of, it can remember all the 60,000 images that you feed it here with, and then what it's training on is sort of like just memorizing everything and then perfectly knowing how to reproduce that, but then not having any sort of, it becomes worse at recognizing the task in general because it's too focused on the training samples. So there is some sort of balance. You need to choose the parameters in a way that you need to have like the right balance. Not too many parameters, so the model cannot cheat and remember everything, and not too few parameters, so that the task is too complex for the model. And the way how you figure it out is actually just you have to try, and then you have to train a model with different sort of architectures, different parameters here, different number of layers even. Yeah, and the complexity just rolls on from there, so you can add some other layers which do some tricks to this as well, which we will sort of mention next class. And so the space to like how many possible types of architectures you can have is really wide. Basically, it's infinite. You can figure out as many architectures as you can as you want, and this is a hard task. I think there are even some algorithms that are trying to like sort of just generate architectures and then try them, and so it's automatically doing all of that instead of you, like meta optimization. Optimize the best architecture for the task you're creating, but that's like dark side that we don't have access to yet. Okay. Yeah, did that make some sense? Did it help? We have to try,
absolutely.
basically. Yeah. Okay, I will recreate this model. And so this is sort of like having the model, but I have not even decided yet what to, like how to actually train it, or I have not shown it any data yet as well. So we will do all of that. We have a model, and we want to kind of set it up. So you remember we were talking about something called gradient descent as an algorithm to like an approach to update the weights in a way that they can teach that they can learn some sort of the data in a way that they are minimizing some sort of error. And in this whole spiel, there are two things that are sort of that we need to figure out: what is the error, and also which algorithm we will use to do this. So one of those things is called the optimizer. So the algorithm that we will be using is called the optimizer, and the error that we will be using is called the loss. So there are a bunch of possible choices there or options there. For the optimizer, for example, this is stochastic gradient descent. There are other types like mini batch gradient descent. There are other algorithms totally which work on a different way, which is called, for example, RMS prop, or there is one called Adam, and which works particularly well actually for some types of data. And yeah, this is this to some degree it doesn't really matter because it will just learn with any one of those options. But you sort of, when you're doing a task, you sort of have to try just bunch of them and see which one of those algorithms works the best for your task. Yeah. If you can make that choice, actually. Right. So the second thing to choose is the loss, and that is the way how you are sort of measuring the distance between the I guess I will refer to the slides. How you measure to the distance between what you are predicting and what you are what you want to predict at the end. I had it here somewhere. Right. So yeah. So something like how you compare the distance between the predictions and the labels. And well, we wrote it like this, and this was a simplification basically, because there are multiple ways how to compare the distances. If we go back here, a thing to note is that we are predicting a vector of 10 and then comparing it with another vector of 10, which is the label. And then this happens not only with the one image that we propagated in, but maybe with all the images, or maybe with some smaller set. So maybe 32 images that we push through, and then we want to compare these labels with these labels and somehow calculate the error. Okay, so there are multiple ways how to calculate this distance. And basically, we will be using one of them, which is called categorical cross entropy, which is using this formula. And then another option, like the basic one, which is super simple to understand, is to just look at the square distance. So this would be the n classes in the vector that we are predicting, because remember this one, this y is size of 10, and this label is also size of 10. So we are sort of going one class by class and then computing the distance and then looking at the square of it. So that would be sort of the mean squared error, because you are then dividing it by this. So this one is the one which is slightly more easy to comprehend. There are different formulas. For example, the cross entropy, which is something which comes from probability theories, and so I will not go into that too much, but more or less all of them do the same thing. So they should give you a large amount, large number for two prediction, for a prediction which is really far from the vector of the correct answer, and should give you some very low number for a prediction which is really close to the prediction that it should be. So the label. So all of the errors basically do this thing, but there are different approaches how we are measuring these vectors between each other. And so some of them might, for example, be really strict when you are getting a prediction which is really far away from what you want, and some may be more lenient in the sense that you have more. It's okay to have some types of mistakes, right? Yeah. So actually, we don't have to care about all of that. We basically usually just choose one or the other, and then if it works, it works. If it doesn't, we can sort of have a look around in Keras. And so there is Keras loss functions, there is a whole web page dedicated to different types of losses. And so this is just a list of all possible losses that you can have. And so we would replace whatever we have here, this loss, by actually like putting one of these in. I think the way how you do it is actually like copying it in like this. Right. I think this would refer to the function already. Right. So we will not do this here because it's an example, but we can sort of replace and play around with it. The same way with the optimizers, if you just search for Keras optimizers, there is a whole web page dedicated to optimizers. And so these are the algorithms that are used to get the best, to minimize the errors. Right. Adam, I was talking about, and Adam, there is a lot. So again, the reason why we are using something like Keras is because we never had to really write any of these on our own. We can just use it as like one-liner here and then change that. Okay, so still we need to somehow dedicate at least like one loss, one error function, and then choose at least one algorithm which will be used to train the model. So this is stochastic gradient descent. And then we also want to somehow see the progress of the model. So metrics is something that is just for debugging basically, or like additional information evaluation. So we don't use this in the formula, which will be updating the neural network during training, but we still want to see something like accuracy. And so accuracy is another formula, and that is basically telling us what's the percentage of the predictions that are correct. So it's again sort of, you can either look at the loss and try to like see how it's getting down, or you can look at the accuracy and see how it's getting up. Okay. Right. So yeah, this is us setting it. So we do model.compile, and so this is sort of like, okay, I made the graph here. I created this sort of like just empty graph for now. In here, I actually build it, so I associate it with its if it's with its loss and with the function that will be used to optimize it, etc. And then we can actually finally use it. So the way how we are going to use it is to fit some data in it. So basically train it with some data. And I guess conceptually this was the most complicated step, because we have to set it with all sorts of things and we don't really know what these are as well yet. So yeah, just like carry on with this. Let's just say that these work. Okay. The way how we train the model is simply with model.fit, then the x data, and then the y data. So we can basically, well, we prepared these before, right? So these are the nicely already shaped data, which we know we can feed to the model. So I am calling sort of like model.fit and then give it this vector or these vectors and then give it these vectors, and it will figure out everything there, everything that it needs to figure out and train with it. So let's just run it run it once. So what happens here is you can see a output which is sort of giving you, there was a number going up into 60,000. So it was going through every one of those training samples, and it was teaching that sample to the model. This was over time changing the loss and the accuracy, but this is something that has been just measured on the training data. So we sort of can expect that the loss will go down and then the accuracy will go up. After one epoch, you can see here, it went, the accuracy went to as high as to 84%. So if we copy this here and then repeat it, this is the second epoch that we are training it with. The loss gets lower and the accuracy gets higher. So the same way as before when we were doing model.add, it always does remember the last setting that we ended it with. So this model was fitted with the first sort of like, it was basically, it went through one epoch of training here, and it still kept the whole setup for the parameters. And when we call it here, we are training it for another epoch. And so obviously doing this one by one is not the most efficient way. So if I hide all of this and then uncomment this one, we will train the model, so fit it, for 15 epochs. I think I have to actually, or just for just for the purposes of showing you how this is working, I will just recreate the model. So I'm restarting all the weights. So we are not sort of reusing the ones that we just trained it with. Okay, so now we will train it from scratch again for 15 times. And then in this case, we will also be using the validation data, which means that after each one of these epochs, we will also try to test it with all the 10,000 samples in the taste data and then get some error there. And okay, let's do this. This will actually take some time. I mean, we are not even running it on GPU, and this is just a MNIST dataset, so it is really fast. But usually this is the slowest part of the of your research process or of your experimentation process with neural networks, because you have to train them. And so it loads all the data and then passes through the network all the data to one side, then updates all the weights going backwards, and then repeats this again and again. So this can take hours, this can take days even, especially when you are working with high resolution images. So maybe what you can see here is that the over epochs, this is kind of like, this is a very messy debug because it's spelling out a lot of numbers, but it could be worse. You can somehow see that the loss here is slowly getting better and better. So this is sort of accumulated loss across all the samples that we are feeding it with. And so this means that the distances between the predictions that the model is making and the predictions that it should have, the labels, is getting smaller and smaller. And you can see these two parameters, loss and accuracy, which is kind of getting the information from the training data, and then the val underscore refers to these two validation sets. So you can see that while it's actually training on the training data, it's also getting better at evaluating the validation data. So the val loss is also getting low. Yeah. So basically, we just want this number to go down and this number also to go down. I think I will get into more details about what can happen with training and validation data next class as well, because I think it's something to explain too. Okay, and so while loss was going down, the accuracy was going up. So this means sort of the percentage of the data set that we are able to classify well. And so this is 84% after just one epoch, 92 after two epochs, all the way to 98% on the training data. You can see that, well, it's, on the test data, it's doing more or less the same way. It ends up on around like 97%. Well, this looks good because on 97% it will be correct. Actually, the MNIST dataset is really easy. So people have like 99 point something percentage there even. So 97 is not the best, but for our simple model, this will do. Cool. So we have ended up with a model which knows all of this. We can. So if you, for example, like forget to add this one here, you can also just call model.evaluate, and it will do the same thing as we as happens here with the validation metrics. So at every moment, this one was kind of recording it with every fit. With every epoch. We can also calculate it once more at the end, and it should arrive to the same numbers. So this validation loss is 0.087, should be this thing, 0.0787, and this validation accuracy is the same one as here. So 0.97% is the same as here. Okay. So this looks good right now, right? We have trained it up to accuracy of 97%. We have some reports that tell us that the accuracy is really high, which is cool. We can even, if you remember, I was saving all of this into a history variable. And if I look into history.history, I mean, this is not the best, but anyway, this is how they implemented it. There is a array, I mean, actually dictionary. So if I look at the keys, it will tell me which values this dictionary has, and it has the values of, or keys of loss, accuracy, validation accuracy, and val loss. So I can also print out just the, let's say, just the losses, and just loss. Interesting. Oh yeah, actually, yeah, that's correct. Because I just misread. The first line, this thing is outputting the whole history. So if I just hide it, in the second line here, these numbers are what I was getting here in this row. So all of these losses. And why something like this is important to kind of isolate. So maybe let's say losses equals this thing, and then I saved it for later. Is then because you can eventually start plotting these and have a sort of visualization. Yeah. So allow me some sort of like inconsistency here. I will jump all the way back into a solution code where I have had done this, and then I am working with this with the history.history, and just to be able to plot it. Okay. Okay, hiding all of this. Okay, so here we are accessing the same like the history.history object, and then getting those numbers. Epochs is not defined. Okay, epochs was 15, I think we were training with. And so as a result, we get some plot like this, which is this is better readable than just looking at these numbers, and it's sort of giving us the same information. So the losses, loss and validation loss, are going down. The accuracies, the accuracy and validation accuracy, are going up. To understand theoretically what's happening there, I will probably explain it in the class later. What can happen and what it means that something went wrong with this plot. This plot is nice because everything is going down and everything is going up, so we have no problems there. Okay, so if I tell you now that we have trained the model, it will be really nice, but you still have to sort of figure out how to use it, because yeah, why else did we train it for? And the way how you use it actually is that you call model.predict, and so in here you will have to give it the sort of image data. So one sample, which is the something from X. So to get that, I wrote this here. So I am getting the image of some number. Let's say this is the 20th image in the test set. I am looking at what the correct label should be. So this is something that the model doesn't know. I will just show it. So print it out visually. Let's do this actually. Let's start with this. And so this will just show me the label and the image. So I will feed the network with this 9 and then convert it into something that it understands. So just put it in a list and then have the model predict it. So the model is predicting from this as a list of numbers, and it will give us a list of predictions. Because we gave it just one item, we will look at just the first prediction, and we want to see what that gives us back. So let's see. So this line, we predicted blah 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 something, is basically this output. So it tells us we predicted, and this whole thing is the vector, which is the 10 numbers that we expect at the end of the model. So it's like, this is the, I'm not saying probability because it's not probability, but this is what the model thinks, how confident it is that this number is 0, very low. How confident it is that this number is 1, very low. all the way to how confident it would be that the number is 9, the last one, well, this is still quite a small number. This means that it's multiplied by 10 or by 10 powered by minus this. So it's some very low number. But in this case, actually, yeah, it evaluates it to almost 1. So this is all of these are really low because these numbers are really small. Well, this is really almost incredible. So that's why I went for all of these numbers and then rounded them into something that we can actually read. So let's see it with 3 digits. And so these are the predictions that the model is giving us. So why are there 10 predictions? Well, we can sort of show it off here. So if we, let's say this was a 9 somehow, then yeah, this is a very messed up 9 now. So the predictions that I'm getting are all of these numbers. And actually I managed to fool this one model because it's now thinking that this is 3 or 5, not actually 9. And this means that it's giving me numbers here and here. Well, let's like give it something easy. I think this one is really good with 3s. So this number here is some low numbers with everything, and then some really high number here in the category where the label should be 3, which is the same as what we are getting here. Okay, so let's try some other numbers. Let's try like the first one. Let's see what it does. Okay, so we predicted for this 2, we are predicting the 2 to be 99. So again, 2 is the strongest. The model is the most confident about 2. I think I found some like messy numbers. So maybe 22 was like a messy 6. Well, yeah, it's still connected it with 6. I think then I wrote down that 1033 is a very messy 8. But yeah, it's still, again, it's correcting this being 8. So we can try for a bit, find some number which would have some, yeah, this is really very sure about this number being 2. Okay. Yeah, still, I'm trying to figure out a number where it would be more kind of split more equally into the different predictions. I think so, because we trained the model all the way to here, I'm getting more or less correct answers everywhere. If I sort of stopped the model in maybe after just one epoch, I would start getting not really perfect predictions here. Yes, this all again. Yeah. Anyway, so like this is just to illustrate a little bit. If let's see, I think maybe this one was slightly nicer. Yeah, at least there are some like activations here and here, so maybe there is some really small amount of confusion. So if we just plot these predictions, then we see that there is really small amount of confusion for 3, but still it's very confident that it's 8. So this is just another way how to like show, not in numbers but in a graph, these predictions. Okay, cool. So basically this is it for using the model. Any questions with this, actually?
Oh yeah, I remember I had a question. So if you go to the cell where you trained the data, trained it on data. So one time you provided the validation data, and the other time you didn't. So what exactly was the difference between those?
Okay.
And like, how does it train like without if you don't provide the validation data?
So it never actually trains on the validation data. So this here, if I edit, it will just kind of in the outputs, it will also give me this information. But regardless of if it has the validation data or if it doesn't, it is always training just on these 2. So I'm sort of giving it this set to train on and then test on something else. And so I don't have to do this. I can train it on all the data, but I don't. In that case, I don't sort of know how well it would generalize to something outside of its training data.
Okay.
Yeah.
Okay.
Yeah, I wanted to start with like the easiest notation, and then with just this command, and then sort of get into the more complicated one.
Okay, so yeah, in the first one, you would just use other data as validation data, or
it would just it would be. I can
just
show you. It will do the same thing, but it will not give you any output about like. It will not give you any information for the validation data, right? So if I do this versus.
I see.
Even the same thing with. I mean, now I'm just retraining again and again, so like the accuracy will be the same sort of, because I'm not restarting it. But the only difference between these two lines is that sort of after the training, it will have a one more run to just calculate the losses and accuracies. Basically, it will run this command, this thing over here. So yeah, it doesn't really matter that much. Yeah, it's nicer to have everything here because then I have the history object and then I can sort of like work with that and plot it nicely. If I was training it epoch by epoch, I am losing the overall information. But the model is still training the same. Okay. So I have one more like bonus session after this, and that would be looking inside the already trained neural network, which is sort of like trying to get all of these intermediate values. Because in this visualization, what is really nice is that you can see this these dots brightly lit if they are activated with high number, and then you can see some of these connections being brightly lit if there are if the weight set there is pretty high. So sort of these lines will be there regardless of whatever the input is, but these activations will be changing over the time. And so the last activation, like the easiest activation I'm looking at is actually this one, the prediction. So this is the output of the last layer. So I get this by just saying, hey, model.predict, and then it will give me the outputs of the last layer. So here. But let's say that I wanted to make this website as an application just to show off how my network is working. I would somehow have to kind of go inside the network and maybe get the values that are the activations here, and also get the values of the connection strengths here. And yeah, this is like a bonus, so maybe there is a bit more complicated code, but which we would anyway just copy and paste probably when we are trying to use it. So yeah, let's see. I will add like model.summary here just to see what we ended up with. Our model was using sequential 5, dense 13, 14, 15. So the reason why the names have these added is because it's always like creating a new one, and it will keep the older one in the memory. So I would have to probably somehow restart it and just delete everything in order to have new names here. But let's say that we want to explore what this layer called dense 13, so our first layer in this network, is actually doing. And so I would change it here, dense 13. And then I'm interested in seeing its own output. So these 300 numbers which are going out from it, I want to see it. So the way how you do it is that you create a new model and say it that sort of like create the new model from the already existing model and tell it that the inputs are whatever this model's inputs were. So basically start here and then say that I'm satisfied with having the outputs of the layer of this name and its outputs. So I'm sort of cutting this already existing network, cutting it up and making a new network which would be just consisting of these two blobs. So it's a neural network operation or something because I'm cutting it out and looking at the intermediate output. And so I created the model here, and then let's still just like, I'm creating the model here and then predicting it. It is with the same way, basically feeding in some images. So I will feed it with the same image I was testing it on before, and then just look at what this output is and its shape. So if I run this, it will give me, for the one image I gave it, it will give me some 300 numbers. And basically what this means is that this input in list was my drawing of 3, basically, or whatever the number. And the 300 numbers are these values for these brightnesses. So how bright this is, the output value Jesus, 1.18 is the first output activation there. So if I look at these and then maybe print like its first, I mean it already is a 2D array because I am feeding in a list, so I have to get a list out. So this is just telling me, okay, I want to see the first for the first image I gave it, and then actually this will be the first neuron output as a number. It's 0. Okay, let's see the second one. It's again 0. Let's see the last one. Okay, there is some activation. So this means that the last neuron here for that number has some number which would be some, like this output here would be not 0.69 but 0.78. Okay, so to show how this is working, I was saying that we are sort of cutting up this already existing model. We are actually creating a new model from these two layers, and so dense 13 input and dense 13. You can see that this one is exactly the same as what we had here, dense 13. The dense 13 input is just sort of like a debug information. You could see it in the plot that was not just textual but the image plot, the one all over here somewhere. Where is it? This one. If I show it, then you can actually see the dense 13 input, dense 13. So in the neural network operation I'm doing down there, I'm sort of getting these two, cutting this one out, and saying, hey, I no longer care about these two at all. This is my new network. Okay. So this is useful to get some sort of intermediate outputs, and I guess use these outputs for visualizing. What you can also do is not only look at the activation numbers, but also actually access the exact weights that you set it with. I mean, that the model figured out to be set up with. So instead of just looking at these, like how brightly these 1 pixels are, you can actually get the information of how strong each of these connections, so each of these lines, which I cannot show on with my cursor because if I'm moving with the cursor it disappears. But all of these lines that are here, they have their own particular number, and that number is the parameter that the model is trained on, sort of. So while the activations, these change depending on how I change these. You can see like this one is always changing depending on how I'm editing the image, these activations. But in theory, all of these weights should be the same. So if I look at 3, there is a really strong one here. If I erase it and look at 3, there is still really strong one here. What it means is that when it was training somewhere originally, what I'm even drawing anyway, it sort of learned that the relation between this neuron and then this neuron should be really strong. I mean, this is really hard to then translate into some like intuition that we can understand as humans, but it sort of is maybe interesting for visualization. So for this, okay, so how to do this manually is, or in code actually, is with these two commands, or with a command dot, which is called get weights. So I will look into the original model, the first one I had, dot get layer, get this name already, which we already started sort of exploring here to cut it up, but here just to get the weights, and get the weights. I will then unpack these weights into W and B and then print it out. Well, let's run it and let's see what this means. W are all the values for weights in let's find a W are all the values which we have sort of here at the start. So all of these possible, like we call it W1 all the way to W6 and then U1 to all the way to U6. All of these weights would be sort of stored as weights of this one layer. So if I oops, it's not the best here. If I look here, W will be will have the dimension of how many inputs it has times how many neurons I have. So this is in total quite a lot of numbers. And then bias is the sort of the stuff I wasn't really explaining that much in the classes, and that means that every neuron also as well has like one additional number that it adds, and that is a 1 multiplied by whatever the bias number is. Well, this one is not that important. What is important is that we can sort of read out from already trained network what its weights were, and then look at all of these values. Right. We can even like inspect the whole model and then always print out the name of the layer and then what the weights would be there. So we can see that the dense 13, 14, 15 had weights of this dimension. So quite a lot of weights there, quite a lot of weights there still. And again, quite a lot of weights here. I think the usefulness of this would be, again, to just somehow visualize this. So I think somewhere in this application that they made here, they were accessing these weights as well. So they had to read out from the model the value and then sort of visualize it here. The sort of more interesting conceptual stuff which we can do is that we can get these weights and then sort of mess with them and then return them to the network. Which means that we can get the network, train it on something, get all the weights, maybe set them to 0, and then sort of see, hey, and if I return this back into the model, if I mess with this model, if I hack it, sort of, what does it do? And well, I guess this is a relatively boring task because we are just identifying whatever this number is, right? This is not a really creative moment. I'm just classifying it with one label. But if I had another model which would be generating something here, being able to mess with the weights inside it would be a possible way how to sort of interact with the network. So let's say I trained it on something which generates me images, and then instead of like, there are ways how to interact with it, but you can sort of like start messing with it, start directly accessing the weights and changing them in order to sort of change whatever it's generating. And I think in that case you would get to the glitchy areas, and maybe those are sometimes interesting as well. So how to do this? When we were using get weights, in this case, we will be using this one, the set weights. And so in here I didn't want to mess up the model we already had, so I saved the model into some temporary file and then load it again. And so this is the lazy way how to make a copy. So let's have a copy of the model. Let's try the first model with some image, which is here. Let's predict what this model will be saying, and then sort of let's mess up the other model, the copy. Let's set the weights to, let's say, 0 times that, and let's see if the hacked model is saying something different, because we will use the copy of the model to predict the same way. And right, oh yeah, I'm accessing a layer which is not there. Let's see, 13. So yeah, so actually, yeah, if I just leave all of these weights the same, the predictions will be the same. So my original model is saying 0, my hacked model is saying 0, because there is no difference between them. If I somehow start changing the weights, so maybe lower every activation in the, remember B is 784 times 300 numbers. So if I start changing these somehow, the one is that these prediction numbers will get different, and also the final prediction number will get different. So yeah, again, this is kind of not really useful now because we are just working with a classification network. But in later cases, this could be a way how. So if you remember the example from the first class from the lecture, where I was showing some work by Mario Klingerman, who was sort of hacking with neural networks. So maybe have a neural network which is sort of creating faces, but then somehow hack it, and so the faces it's creating from then on are sort of like messed up. So this would be one way how to change these models. So yeah, this is just a bonus. This code is, I will not go into explaining what everything all of does exactly. It's a bonus if you want to sort of like play around with it. If you ever need to sort of explore this in a clean way, you can look at the solution code where all of this is kind of everything that we have been doing here is there as well, but we have in this case is more sort of more legible with less commentary, but also basically the same functions, but just adding everything together. So you don't have to run every one of those boxes on its own. You can sort of train them in a or run them in a better way. For the next class, so next week, I will talk about sort of the additional steps that we can use to make our models work better, and quite a large one, basically one which really brought the revolution in the usage of AI and neural networks and deep learning was the use of convolutional layers. And so we will explore all of that, what that means. We will talk about the first model that sort of made the whole revolution happen, because it was a really famous model which worked on a competition and somehow scored very high score when compared to previous methods. And so this was in 2012, and since then a lot has been added to this as well, but we will talk about these small kind of improvements that have been made. And the convolutional layers especially are quite important for us later as well, because it's a way how to work with images in a way which has been inspired by actually our own visual system, and so it's quite smart usage of that. Okay, in the practical section, we will try loading some of these and then having an already trained model and then using it for something. So being able to sort of maybe predict with the model that has been trained on recognizing images and have it tell us the answers for some new images that we give it. Okay. This homework, please submit the answers into the quiz. I think the quiz for this week should already be there. I copied this or like a similar slide there as well, so you should have some description, or you can look up in the slides for more details. And that's basically it. So that's the end of the second week. Awesome. So yeah, take care. See you next week.